In the last video, we were just talking about how ions or charged particles are experiencing the effects of two different forces. A chemical driving force that's due to their concentration gradient, and an electrical driving force that's due to charge-charge interactions. But remember that each ion has a unique concentration in the extracellular and intracellular fluid. And additionally, ions can be either positively charged or negatively charged. And within that, some of them can be monovalent or bivalent. So this means that the electrical forces that are acting on every single ion are also unique, just like concentration gradients are unique. So as a result, the balancing point between concentration gradient and electrical potential is different for every single ion. In other words, every ion has a unique equilibrium potential. Equilibrium potential is the voltage that that ion would create across the membrane if we were to allow those two forces to be balanced until they were equal and opposite. And the net flux of that ion across the membrane would be zero. Equilibrium potential is abbreviated E sub x, where x is the ion that we're talking about. Now, before we go too much further, I want to stop to address one common misconception about these potentials that develop across the plasma membrane. I mentioned to you earlier in the course that I'm originally from Buffalo, New York, and that means that I grew up about 5 minutes from Lake Erie, which is one of the Great Lakes. I absolutely love being near the water. In fact, it's one of the reasons that I still live on the shoreline here in Connecticut. So I promised myself that no matter where I ended up, I would always be in a place that wasn't landlocked. I wanted to be close to the water. And so under normal circumstances in the summertime, I'm kind of a bit of a beach bum. Don't worry, I wear lots of sunblock, and I'm usually the guy that's reading a book inside of a pop-up tent, which delights my friends and the people around me. Anyway, I can't stand swimming in pools. Going to a pool party is like a circle of hell for me. And the reason is that pools are gross. People don't shower before they go in the pool, and their filth goes into the water. Little kids pee in the pool, and then I have to swim in it. It's just completely gross. But of course, the ocean is totally fine, right? Nobody thinks twice about peeing in the ocean. The fish do it all the time. And that doesn't really bother me. The difference between the ocean and a swimming pool is the relative volume. A swimming pool has a small volume, and so I'm much more likely to be swimming in someone else's pee in the swimming pool than in the ocean, which has a comparatively larger volume. I guess I'm going to switch my example to make things a little bit less gross and unsettling. So if I have a glass of water and I add a drop of blue food coloring to it, the water is going to turn blue. But there's almost no chance that I'm going to make the ocean more blue by adding blue food coloring to it. The volume is just way too big. And in fact, if I did add blue food coloring to the ocean, the only place that I would actually be able to see a change in color was at the exact spot that that drop of blue food coloring hit the water. The cells inside of your body are like the ocean. As things start to get more complicated, as we move through this unit and into the next one, we're going to talk about movements of ions through channels. I want you to keep all of this in mind. The relative concentrations of ions almost never change under normal circumstances inside of your body, even when channels are open. That really only happens in disease states or in the laboratory. And that's why it's so important for you to memorize the relative concentrations of ions that I talked to you about in the earlier parts of this unit. But thinking about the food coloring example, this also means that when ions do move, they can create big changes in voltage, but they don't create changes in voltage for the entire cell. They only change the voltage at the plasma membrane, right, where the food coloring is being dropped. That's the place where the ions are coming into or moving out of through channels. And this is the reason that we use the term membrane potential instead of something else, like maybe cell potential. So in the conceptual examples in the last video, you saw ions moving around, trying to balance their concentration gradients and their electrostatic forces. In the very last example, we ended up with a situation where neither of those forces was completely balanced. And that's the place where those conceptual examples really start to break down. How do we actually know what it looks like in terms of the number of ions? We don't know how many ions there's going to be on either side just by looking at a PowerPoint animation. If we wanted that information, we would need to use this equation that we're looking at here, which is known as the Nernst equation. That would allow us to actually calculate the equilibrium potential for that ion. In other words, the Nernst equation is used to calculate the voltage that would develop across the membrane if an ion was allowed to move until its concentration gradient and its electrostatic forces were balanced until they were equal and opposite, and the net flux of the ion was zero. It had reached a steady state. So this is the reason why the other name for equilibrium potential is Nernst potential. It's derived from this equation. There's a third name, which is reversal potential, but I don't use that term because it's usually more appropriate for a lab setting. I want to mention for the third time that equilibrium potentials are unique to each ion because each ion has a unique concentration gradient and a unique charge. And so whenever we use this equation, we're always considering only sodium or only potassium or only chloride. The Nernst equation looks a little scary, but it's actually just a mathematical representation of stuff that we've already talked about in the earlier videos. And we can see that if we unpack each of the terms. So the only assumption that we need to make when using the Nernst equation is that the ion that we're talking about is completely permeable, and it's the only ion that's permeable. So the Nernst equation says that the equilibrium potential for an ion, which is E sub ion, is equal to 61, which is a constant, don't care about that, over Z, which is charge. The 61 refers to temperature, and it's always constant in the equation, so again, don't care about it too much, unless you're actually doing the calculation. And you'll never have to do the calculation, so no calculators are required for this exam at all. But Z represents charge. Charge is important because ions like sodium and potassium have a positive charge, so Z would be 1, plus 1. Ions like chloride have a minus charge, so it'd be minus 1. Z in this equation is telling us that equilibrium potential is affected by charge-charge interactions, but we already know that from the previous slides. The next part of the equation is the log of the concentration gradient for that ion. So it's the outside concentration over the inside concentration. This part of the equation essentially tells us that concentration gradient is important for equilibrium potential, but we also know that already from the first part of the video. So even though you don't have to do any actual calculations with the Nernst equation, because we're thinking about it only as a concept, there is one little bit of math that's worth pointing out, which is that the log of 1 is 0. And that means that if the ions have equal concentrations on the inside and the outside of the cell, a number divided by the same number equals 1, the log of 1 is 0, so equilibrium potential is 0. And this helps us explain that second conceptual example that we looked at before. So here's the table that we looked at earlier showing the relative concentrations of different ions inside the cell and outside the cell. If we were to plug in those specific numbers along with the charges into the Nernst equation, we could calculate a unique equilibrium potential for each of those ions under normal conditions. But we've already done that for you in the column on the right-hand side of this table. Now, once again, it's really helpful to memorize that potassium has an equilibrium potential of minus 75 millivolts, that sodium has an equilibrium potential of positive 58 millivolts, and that chloride has an equilibrium potential around minus 59 millivolts. But at a minimum, you want to remember that potassium has the most negative equilibrium potential, that sodium has a positive equilibrium potential, and that chloride is negative, but not as negative as potassium. Now, from the Nernst equation, we can see that equilibrium potentials normally don't change, except in laboratories or states of disease. And that's because the only things that can affect equilibrium potential are concentration gradients and charge. We can't really change the charge of an ion without a nuclear reactor, and homeostasis generally prevents major shifts in ion concentrations. So again, these equilibrium potentials listed here are good reference points.